-1. All right, today is not the day that isn't loading. Today we want to head back over here to section 12.4. We'll be looking at the cross product. Uh, so last week we didn't quite finish exactly everything that we had planned. So start with just a quick review of that. That's going to happen some days. We just don't have time to get through quite everything. Just because of the way that this is only a 50-minute class period, but probably talked about the stuff for way too long. So I'll try to speed things up. But the thing that we skipped at the end of last week was orthogonal projection. So we did all the stuff with projecting one vector onto another one. Seeing if you would just, there you go. So we were projecting one vector onto another one. We called that the standard vector projection. The leftover bit was the orthogonal projection. And the best way to define that orthogonal projection is by simply comparing it to the regular old projection and saying that it's just the difference between the original vector and its projection. Makes a lot more sense if you look at it visually. So let's just do that. And maybe we look at this example because it shows what's going on maybe a little better. So if that blue vector v is the vector we're interested in, I'm projecting it up to that gray line. The yellow vector is that projection. So it's the part that actually gets projected onto my secondary vector. The orthogonal projection is just the part that's left over that completes the triangle, that magenta line B. And we call it the orthogonal projection because it's orthogonal or perpendicular to the vector that I was comparing to. So that vector I'm projecting onto, my orthogonal projection should be orthogonal to it. And also, what else should I say about that? If we take the projection and the orthogonal projection and add them together, we get the original vector v, right? We just follow the yellow vector, then the pink vector. We end up doing exactly the same, or we get to the same point that our blue vector v was going to. These two projections make a lot of sense when we compare them to the vector we are projecting onto. So one of them is parallel, the original projection is parallel to our onto vector. The orthogonal projection, of course, being perpendicular to our onto vector. And one final definition that I was going to write down in class is that orthogonal vector, that orthogonal projection, is also equal to our mystery vector b, or the vector that we care about, b, times the sine of theta, being the angle that is in between vectors a and b. So where the regular projection was b cosine theta, the orthogonal projection will be b sine theta. And I think if we just take it back to trigonometry, that'll make a ton of sense. Because that guy right there is our angle theta. Our regular projection, the yellow one, is the adjacent side to that angle. So adjacent is cosine. And our orthogonal projection, the magenta one, that thing's opposite. Opposite being sine theta. All right, cool. So that's a quick 5 minutes there. So now let's start the cross product. So cross product is going to be another way of multiplying two vectors together. This time, instead of just multiplying them straight down the line, we're going to do these fancy crosses through the product. So the easiest way to visualize one of these cross products or to calculate a cross product is that it is the 3x3 determinant, or the determinant of that 3x3 matrix drawn up there. IJK across the top, our vector A across the middle, and our vector B across the bottom. So then A cross B, again, determinant of that matrix, which is drawn out in this line in front of us right now. If you want to solve the 3x3 determinant, the best way to do that is to break it down into smaller 2x2 determinants, and then you just do a cross product, which means we multiply down that way and then subtract multiplying down the other way. So 2 times 0 minus 3 times 1. And then we do the same thing all the way down. We go that way, then that way, and then that way. Multiplying those crosses gets us the numbers that we see written down below. So again, that's 2 times 0 minus 3 times 1. Then it's 3 times -2 minus 1 times 0. 1 times 1 minus 2 times -2. And then just for clarity's sake, I'm going to remove these crosses so you can see it a little bit better. Another way of writing that out so that you don't have to break it down into each of the smaller 2x2s is that you can write out that 3x3 again. Just over to the right, because we can just have this pattern repeat itself and draw those same crosses through, figure out how we're multiplying stuff together. So we're about to do just another live example in a second. Don't spend too much time right here. But again, when we're starting from the upper left and going down to the right, those are going to be all of the positive entries in this cross product. Whereas when we start right and move down and left, that's moving backwards. So all of those will get a negative value associated with them. Some other fun elements about expanding these cross products. None of the components that are in the X position end up in the X result of the vector, in the X resulting vector. So let me try that again. If I'm looking at the result of this cross product, the one on screen, there's a -3 for the X value. But the numbers that I used to make that 3 were the yellow and pink ones highlighted inside of that matrix. Right, with purple being the ones that are in the X component, and those purple numbers did not contribute to that -3 in any way. Right, so I got the I part from up at the top, meaning that's selecting it's going to the I position in the resulting vector, but not any of the purple numbers. It was all built up of yellow and magenta. Same thing for the Y component of the result. It won't use any of the yellow numbers. So I can use anything from the Y positions of the original vectors. And then the Z component won't be using any of the Z components of the original vectors. None of those magenta numbers make it in. But again, more on that. Just go do an example in a second. To just further define what this cross product is. It's going to give us a vector that is orthogonal to both A and B, or perpendicular to both A and B. And the result this time is a vector, which will differentiate it from the differentiating this cross product from the dot product, where we multiplied two vectors together and our result was a scalar, or just a number. When we take the cross product of two vectors, we're going to get another vector as its result. If we want to take the magnitude of the dot product, that'll be the same as the magnitude of the two original vectors multiplied together times sine of theta, compared to the dot product, which gets us the magnitude of the two original vectors times cosine theta. So some fun parity going on there. And if two vectors are parallel, then their cross product will be 0. Or at least the magnitude of their cross product will be 0. The cross product itself of two parallel vectors won't be 0 per se, but it will be the 0 vector. So remember that these things do need to come out, like the result of these cross products should be a vector. So if I take two 3-space vectors that are parallel, take their cross product, the result would be 0, 0, 0 instead of just 0 all by itself. Again, slightly pedantic, but if you try to type that into WebWork, it'll get mad at you. So make sure it's the 0 vector. And then finally, just to bring up the right-hand rule one more time, and then a couple of other elements over here to the right. If you take, we'll do the right-hand rule again, the one where you curl your fingers around something. I'm going to take the cross product of A and B. Then if I start my fingers pointing in A's direction, curl them over in the direction of B, then my thumb has to stick in the direction of the resulting cross product. So if I just curl that way, we can see it in a couple of different diagrams that I've drawn up there. That normal vector, which is going straight up, A, B, it goes in the direction of that sum. Hopefully that visualization makes some sense. Because it's sort of hard to just describe the right-hand rule in words. I think it's a lot easier if you just, there's a picture to go with it. A couple of other things I want to say before I get into the heart of today's lesson. One of those is that A cross B and B cross A are two different operations. So unlike standard multiplication or even the dot product, where we have the, which fourth grade property is it? The one that lets you swap the order of two things that you multiply together. It's not the transitive property. Is that the commutative property? I don't know. The one from multiplication lets you swap the order of two things, right? 4 times 5 is the same as 5 times 4. Both of those are 20. That property doesn't apply to cross products. It doesn't work that way. It's very close though, because if I do switch the order of my cross product, I still need to get a vector that's orthogonal to both of the original vectors, but this one's going to point in the opposite direction. So it'll point down instead of up if the original one was already pointing up. So you could imagine, taking the same right-hand rule, but this time sticking your fingers in the direction of B, but then you've got to curl in the direction of A, and your fingers don't want to curl backwards. You have to turn your hand upside down to curl back in that A direction, which is what gets that cross product vector of B cross A. The reversed order just points down instead of up. So if I reverse the order of the cross product, I just need to slap a negative on my result in order to keep equality there. Sure, I'm going to remember the name of that property like 10 minutes after class. I don't know. If I still have my computer going, I'll record myself saying that. Just a quick chart for a quick reference chart for the difference between the dot and the cross products, or just a holistic look at the difference between them. Again, if I look at the dot product, my result is a scalar or just a number, whereas the result for cross product is a vector. Their magnitudes are both fairly similar, or at least that they're both the magnitudes of the original vectors multiplied together times either sine or cosine of theta. Cosine for the dot product, sine for the cross product. And finally, there's a zero property for both of these products. If the dot product is 0, that means my two vectors are orthogonal or perpendicular to each other. And if my cross product is 0, that means that my two vectors are parallel to each other, which is kind of the reverse if I swap those. If I take the dot product of two parallel vectors, that's going to be the maximum value I can get out of two magnitudes of a particular length. And if I take the cross product of two perpendicular vectors, I'm going to get the largest cross product possible. But I've blathered enough about not doing examples. Let's go do one. So what do we have? 4.6. Finding the cross product of A and B, and then verify that it's orthogonal to both. So here's what I would do if I wanted A cross B. I would say A cross B is a 3 by 3 determinant. I, J, K across the top. A is 1, 1, negative 1. So I'll put it here. And then B is 2, 4, 6. 2, 4, 6. And I want to get a cross product of those things. For the first component, I'm just going to be looking at these numbers, looking at the collection that are not in the I column, and then just go in the positive direction. This looks like 1 times 6. Hey, pen. Come on, buddy. Yeah, there. 1 times 6 minus negative 1 times 4, or plus 4. To get my J component, I need to look at these numbers. But I always want to read from left to right when I'm putting these cross products together. So if I'm doing the J component next, I need to move to the right of that column first. So instead of 1 times 6 minus negative 1 times 2, as it kind of looks like they're set up there, again, I really need to read to the right. So the group I'm looking at here is really more like a negative 1, 1, 2, 6. Because I need to read from left to right to move to the right of the J column. So I want negative 6, negative 1 times 6 minus 1 times 2. So again, negative 6 minus 2. And then, well, we've got one more of these to go, right? Stop. Probably not going to be able to erase that, but that's fine. For the K column, I again have a nice block, so I'll go multiply these guys together. 1 times 4 minus 1 times 2. I believe that's 4 minus 2. And I'm sure someone will catch me if I got any of those numbers wrong. But setting that all up, 6 plus 4 is 10. Negative 6 minus 2 is negative 8, and 4 minus 2 is 2. Yeah, I think that's right. So I want to take the middle one is wrong?
Yeah.
Ooh, how so? I only switched the top. Okay. Heard a bunch of whispering out there, so I figured something was up. All right, so yeah, let's try that again. Negative 1 times 2 is negative 2 minus 1 times 6. Did I get the same thing? Is it right now? Okay. So I just wrote the order down wrong, but still had the correct results? Is that what happened? I don't know. I erased it. If you're watching this video later, go back and see if I did anything. Go back and see if I did anything completely different. But, well, we're about to find out in this next step if our result was right, since we're going to check to see that these things are orthogonal. So I'm going to take the dot product of that result, 10, negative 8, 2, then negative 8, 2, and do its dot product with both A and B. So how about 1, 1, negative 1? And I get 10 minus 8 minus 2, which is 0, I think. And then same thing, but with the other vector, 10, negative 8, 2, dotted with 2, 4, 6, 2, 4, 6, to get 20 minus 32 plus 12, which is 0. So I think our result's correct in the end. Cool. So let's run with that. We'll try the cross product again in the next example and see if it goes possibly any more smoothly. But first, a few properties of these products. Again, we talked about one of them already. If I reverse the order to B cross A instead of A cross B, it's just going to change my result by a negative sign. If I have scalars being multiplied into the vectors that I'm taking the cross product of, I can factor those out. So if I'm looking at, if I've got a scalar R being multiplied into A, and a scalar S being multiplied into B, I can pull both of those out. Just do the cross product of A and B and then just multiply those scalars in at the end. Oftentimes it's a little easier to run a cross product that way. There is a sort of distributive property, just have to be careful about its direction. So if I've got A cross B plus C, I can distribute that A to the B and the C, but it's got to stay on the left side. Because if I look at it the other way, B plus C cross A, again, can be distributed, but now it's got to stay on the right side of each of the vectors I'm distributing to. If we throw this stuff into action, so say that we already know our cross product, it's -2, 2, 1. And I want to calculate part A, 3, 4, -2 cross 1, 1, 0. I would just notice that I swapped the order of my two vectors. Meaning I could just take negative, whatever that result was, -2, 2, 1, which I'll rewrite as 2, -2, -1. Right. If I'm going to just multiply that negative into a vector, it applies to each of my three components. And for the next one, zoom in just a little bit. Very similar looking cross product as well, except that my first vector, which used to be 1, 1, 0, is now going to be 4, 4, 0, which is just 4 times the original vector. So I could call this thing 4 times -2, 2, 1, which would give me -8, 8, 4. So again, I can just multiply that scalar through. All right, and now we're going to get back to another actually calculating a cross product. But first, definition. If I want the area of a parallelogram, it is just twice the area of a triangle. Right? Parallelogram is really just two identical triangles, but duct taped together. The geometric definition for the area of that triangle would have been x times y times sine theta, or maybe a times b times sine theta, if we're going with the a and b labels that we have up here. We can translate that into vectors. And just call it magnitude a times magnitude b times sine theta. And that is going to be equal to the magnitude of the cross product. So geometrically speaking, if we want to get a sense of what the cross product is giving us, I think it makes the most sense to break it down into its two pieces, a magnitude and a direction. For the direction part, we covered that already by the right-hand rule. It's just some vector that is orthogonal to both of the vectors that I started with. That element's important for our cross product. But as far as its length goes, here's the example that we're going to want to use. We want to compare it to the parallelogram that the two vectors generate. Or we'll see in a second, maybe it's easier to just think about the triangle that the two vectors generate. But if we want the whole meaning of the parallel or the whole meaning of the magnitude, we've got to go to the parallelogram since that's the part that matches up exactly. So the more or the larger the area we have between our two vectors, the greater our cross product is going to be. Like if that area gets bigger, then our cross product is going to get bigger. Two ways to make that happen. I either just use bigger vectors, which probably makes sense, right? You know, bigger vectors probably should result in bigger cross product. Same thing with multiplication. If I want bigger results, I should multiply bigger numbers. Basically holds. The other option is that I could get the angle between them closer to 90 degrees. If I want to make the area of this parallelogram bigger, just kind of, open up that space in between the vectors a little more. Of course, that only works to a point because then if you start extending beyond 90 degrees, it'll get smaller again. So 90 degrees is going to be the maximum magnitude between two vectors if I'm taking their cross product. But right. So if that's our geometric definition, let's just go to find the area of these two parallelograms, writing down what they are. U cross V is the vector I, J, K. U looks like 1, -1, 0. And V is 0, 1, 3. So I'll write those together. And let's see if I can do a better job of writing out what my cross product is going to look like. Again, for I, I'm going to take this small subset. So -1 times 3 is -3 minus 1 times 0, which is 0. All right, and here's the tricky one. Can we get it? I'm looking at that collection of 4 numbers, but again, I need to read from left to right. So 0, 3, 1, 0. Okay, there's a lot less whispering this time, so I think I got it. Let's see, 0 times 0 would be 0, minus 1 times 3 is 3. So 0 minus 3. To then go look at the final set, and maybe I'm just gonna leave some of these markings up there now. Let's see, I've got 1 times 1, which is 1, minus -1 times 0, which is 0. Put it all together, what do we get? -3, -3, 1. We could check this thing real quick to make sure that it works. Dot product with 1, -1, 0 is going to be -3 plus 3. That's 0. Dot product with 0, 1, 3. -3 plus 3, also 0. Hopefully you're cool with me just like talking those numbers out. But right, we really just wanted the magnitude of these two vectors. Try that again. U cross V, but I want the magnitude of them, which looks like it'll be the magnitude of -3, -3, 1, which is going to be a square root. Looks like 9 plus 9 plus 1, or square root 19. And I'm just going to leave it at square root 19. As long as that's all right. If you needed to know what that number is, it's more than 4, but it's less than 5. That'll be good enough for us, at least for now. All right, area of a triangle with the vertices P, Q, and R. So I am going to create a couple of vectors. the vectors I want to create, I think are going to be PQ and then PR. So PQ, I'll just take Q and subtract P to get -3, 1, 2. -3, 1, 2. Again, if I want to get the vector that connects 2 points, just take my final point and subtract my initial point. So -2 minus 1, 1 minus 0, and 3 minus 1. If that made sense, then probably PR will also make sense. PR will be the vector 3, 2, 4. Or again, I'll just take R and subtract P. Now I'm looking to get the area of the triangle with those vertices. Here's where I'm just gonna come back up to our definition. The geometric definition of the cross product. And let's, how about draw it in this way? Drawing in the line that just connects the terminal points of those two vectors. And I can see that this parallelogram is really two triangles, as I mentioned a second ago. And if I just give some labels to a few of these points, maybe call that P, call this one Q, and then this one R. And that triangle, PQR, exists inside of the parallelogram. And I think with the way it's constructed, I can pretty easily claim that it's exactly half of that area. Since the dotted line on the other side of that gray line that I drew in should create a congruent triangle to the one that I filled in on the lower left. And so I'll know it's congruent because it's got the same angle, right? It's a parallelogram, so those angles need to be the same. And they share a side in common. And it's the same side in the same position, so I know that their scales have to be the same as well. And then I can further argue that the angles that I just cut into pieces, where Q and R are located, I'll have congruent angles there as well, but I'll leave that alone for now. All of that to really say that if I want the area of triangle PQR, the area of PQR, it's going to be half of the magnitude of that cross product, or of the cross product that we haven't done yet, but that we're going to do, of PQ cross PR. Right? If I just took the magnitude of the cross product by itself, I'd get the full parallelogram. So if I take half of it, I'll get a triangle. I'll get the triangle part. So that means we just need another cross product. So let's go do that. PQ cross PR. Again, I'll do everything in my power to put all of my vector hats on the quantities that I know to be vectors to further help distinguish those between vectors and scalars. So that cross product, I hear a ringing. Well, IJK across the top, -3, 1, 2 across the middle, 3, 2, 4 across the bottom. And see what we get. Looks like I'm going to have 1 times 4 minus 2 times 2, which is 4. Next down the line, 2 times 3 is 6, minus -3 times 4 becomes plus 12. And then -3 times 2 is -6. Minus 3 times 1 ought to be 3. So to just put it all together, I think I've got 0, 18, negative 9. Which, yeah, seems like that works. So I need to get the area or the magnitude of that thing, which looks like it's going to be 1/2 times the square root of 0 plus 18 squared plus 9 squared. And in order to be maximally lazy here, and not have to go get a calculator, okay, so I want to not get a calculator and I want to not square 18. So instead, what I'm going to do is notice that all of the numbers on the inside of my square root have a 9 squared attached to them. So I'm going to factor a 9 out. Right? I can pull a 9 outside of that square root. 18 and 9 with a factor of 9 in them. And they're both squared, so I can remove them. That'll leave me with 0 plus 2 squared plus 1 squared. And I think that's 5. So 9 over 2 root 5. I think that step's sort of optional, but again, didn't want to get a calculator. And I didn't want to have to remember 18 squared. Fortunately, I didn't have to. All right, cool. Hey, and I think we're actually gonna finish the notes today. No way. All right, let's find a couple of unit vectors that are orthogonal to both of these two things. So we already know, excuse me, we already know how to find an orthogonal vector. We know we can just take a cross product. So let's go do that. The cross product I'm interested in. Again, let's go I, J, K. J minus K looks like 0, 1, negative 1, and then I plus J, 1, 1, 0. 1, 1, 0. None of my lines are staying very straight, are they? Hey, stop that. Again, sound effects are very important. If we take this cross product, what are we gonna get? 1 times 0 is 0, minus 1 times negative 1 becomes plus 1. Then we've got a negative 1 times 1 minus 0 times 0. And finally, 0 times 1 minus 1 times 1 is 0 minus 1 to ultimately get the vector 1, negative 1, negative 1. You might even be able to do the dot products pretty quickly in your head. 0, 1, negative 1 times this result. 1 times negative 1 plus negative 1 times negative 1 ends up being 1 minus 1, which is 0. And for 1, 1, 0, dotted with this thing, it's just select the first two components, 1 and negative 1, add them together. I also get 0. It might be a more advanced technique, doing dot products in your head. And it doesn't always work out all that great, since sometimes you get it wrong. So be careful if you do that, I guess, is my advice to you there. But I think it worked here. So what's next? We have our two orthogonal vectors. No, we don't have our two orthogonal vectors. We have one orthogonal vector. There we go. But we want two unit vectors that are orthogonal to the vectors I started with. And the thing I have to work with is a single vector that's not a unit vector, but is at least parallel to my results. Right? If I can find two unit vectors parallel to 1, -1, -1, I'll have done my job. So that's what I want to do. If I want a unit vector, then what do I want? I need the magnitude. So let's just grab that real quick. Magnitude of 1, -1, -1 is the square root of 3. 1 + 1 + 1. I get 3. So if I want my unit vector, I'll go U for unit vector. And it'll be my first one, so I'll call it U1 because I'm just very so creative. And it's going to be 1 over the square root of 3 times the vector I already had. 1, -1, -1. That thing's a unit vector, and it's got to be orthogonal to the original 2 because it's parallel to their cross product. There's the first one. Now I need the second one, which might originally sound like that would be really hard to do until you realize it's actually super, super easy. Just don't overthink it. U1 is just a negative copy, or U2, not a band, but instead a negative copy of the first vector. So just copy and paste. So I just need to slap a negative right there. I think just keeping it on the outside's fine, or I can distribute the negative through. Could be fine either way. So if I need two unit vectors that are, perpendicular to a pair of vectors, I know I can always go get that because it's just going to be the cross product divided by its magnitude, and then just take both the positive and negative direction of that result. So expect that question to show up again sometime. I know at the very least it's a homework question. Yeah, that's our last example. All right. Hey, look, our application of the real world. It's here. Torque. It functions like a cross product. We even have our right hand rule to tell us which way is righty-tighty and lefty-loosey. Those two shorthands for remembering how to tighten a screw or loosen a screw, or maybe it's a bolt in this case because we're looking at torque. I guess screws also function that way, but this wrench makes it a lot easier to describe what's happening. So we're going to go with the bolt example. If you do the same thing with your cross product, where we use the right hand rule, you can also use that to figure out which way your bolt is going to go if you apply some rotational force to it. Because if you curl your fingers to the clockwise direction, which means if you're looking at your bolt that you're trying to loosen, and you curl your fingers over to the left, your thumb points out, which means that bolt's going to get loosened. It's going to come out of whatever system you're trying to wrench it into. Versus if you curl your fingers the other way, that's a little hard. Does it work better that way? Maybe. I don't know. Right hand rule can be tricky sometimes. If you curl your fingers over counterclockwise or to the right, righty-tighty, your thumb points in, which means you're tightening that bolt down. So there's my hand-wavy explanation of how torque works. There's a couple more steps, but that'll do us for now. Torque, back from physics when we were just working with scalar values. It's force times the distance. In particular, it's the distance from your pivot point. And we had the magnitude, or well, let's back that up. If we convert those things to vectors, we can claim that the torque is just going to be the cross product of a force vector and a lever arm vector, so a distance vector. So F cross R. And if we needed the magnitude of that thing, it'll just be the magnitude of a cross product, or force times the length of that lever arm times the sine of the angle that's between them. So torque gets maximized when I'm driving all of my force perpendicular to the lever arm, right? Which makes sense. If my pivot down here is at my elbow, I'm going to get the most amount of torque if I apply my force directly perpendicular to the lever arm to try to rotate it this way. And I'm going to get no torque at all if I try to apply my force parallel to my lever arm, right? If I just apply a force directly into my lever arm, nothing's going to happen there. So if you imagine, sticking this this wrench onto a bolt, if you just shove the end of your wrench, like lengthwise, you're not going to be doing anything. That wrench gets its action by rotating it. So we want to take a perpendicular angle to our lever arm rather than a parallel one. All that to say, if I really want to find the magnitude of the torque generated by this 10-pound force on the end of a 5-foot lever arm, where our pivot is at A, right? We're pivoting at A. If we're pivoting at B, this is, well, we're not going to get a lot of torque if we do that. So pivot at A, and to get the magnitude of that torque, we'll just use magnitude F times magnitude R times sine theta, which in this case is going to be 10 times 5 times the sine of 110 degrees. So we know that our torque is 10 pounds. Our length is 5 feet. So those are going to be both magnitudes. So we actually do have enough units to come up with an answer this time. It's 50 sine 110 foot-pounds, right? Foot-pounds, I think, is our torque unit. As opposed to, what do we usually use? Newton meters is our SI unit. But here we had a standard one. Cool. So with the last 2 minutes of class, because I actually have a couple of minutes, and it's probably only going to be like a minute and 2 seconds by the time I get there. I want to look at a homework problem. So I've worked out some of the commonly missed homework problems, or at least the ones that I get questions about frequently. And this is one that I already saw being asked, so I want to talk about it. This person whose work I just screenshotted and threw up on my notes to talk about, what they did wrong. Sorry, whoever this is. I think they're from different stuff today. They wanted to calculate some angles here. The way that we're going to do that is by using the definition of the dot product in tandem with an arc cosine function. So basically just take the definition of the dot product, but solve it for theta. It's going to be arc cosine of the dot product divided by the magnitudes. And they calculated their 3 vectors, PQ, PR, and QR. That'll be my guess for what they did. Plugged it all in. 2 of their answers were right, but one of them was wrong, and they were really confused as to why. They did the exact same thing in option 2, so why did it only fail once? Well, solid question. So that's going to come to the way that we define vectors. In particular, I want to look at this set right here, this little diagram. If I'm looking to find angle Q, that means I am looking for the angle that's in between the vectors QP and QR, right? I want my initial point for the vectors I'm calculating both to be Q. That's how I get the magenta Q down the bottom. But if I don't do that, and instead use PQ and QR, their initial point is different, I'm going to be calculating not the same angle. We'll be calculating a different angle. That angle Q2 instead is what I would get. Which means I just end up with the supplement to the correct answer if I don't change my vectors around. So highlighted there in red, I really wanted to emphasize that angle Q which should be the arc cosine of qt dot qr over those two magnitudes, is not the same as the dot product of PQ and QR, again, over the same magnitudes. So just be careful with that if you're doing this problem. If you do set it up correctly, I think the actual answer to this problem was about 0.9, or a fancier way of getting there is I can just take pi and subtract the wrong answer. I get the same thing, 'cause again, they're supplements of each other. Yeah, I knew I was going over on time. Cool, I'm gonna stop it here because I already should have. I will see you guys again on Friday. Okay, bye, 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 bye. It was the commutative property. Told you.